Okay, so here we are. Welcome everyone here. Felipe, Hamed. Now I can see you properly, Hamed, but maybe I'm not sure whether the connection will be stable if you have your camera switch on. I'm not sure, but let's see how it works. So, well, I cannot hear you if you are trying to speak because I'm not sure. I don't know. But anyway, so again, let me welcome to this lecture, online lectures at least this week's. Yeah, Hamed, I will mute you because I cannot hear you properly. Okay. So yeah. I'm not sure why I cannot switch off your microphone. Okay, no, it's a bit unstable. Okay, so let me continue. So welcome, and let me show you, share my screen first. And here, this is the course program that I sent you already, so that you can check more in details what this course is about. Of course, this is an introduction to superconducting quantum circuits, and you may probably know or probably you have heard about this quantum platform, which is very, I mean, it's a very hot topic right now, today, these days, in the physics community. For instance, of course, you know, probably you are aware that this type of technology is already used by IBM or even Google and D-Waves, so that I mean, as a building blocks for building quantum simulators or quantum computers. Okay, so then this course, of course, we will touch let's say the hardware of has to be with the hardware of the quantum computers made of superconducting systems. That would be the analog of studying the transistor. Okay. As a first, let me, well, of course, you know already, I mean, here I put some requirements for the lectures. Of course, you all of you have a course in quantum mechanics. So essentially, this will be applied quantum mechanics most of the time. You need to know some basics notions of electromagnetism. You will see later that, I mean, with undergraduate studies will be enough to really understand the way we will treat the circuits. Okay, and you have to know, or you have to remember about capacitances, inductors, and as the case of a linear component in a circuit. Later on, we will establish, or we will introduce the most important part of the well, one of the important parts of the superconducting circuits, which is the Josephson junctions, because junctions will provide the necessary anharmonicity in our system. And a consequence will be that we will have harmonic spectrums in the circuit. And that will be important, because then we will be able to implement quantum gates, essentially. And in general, as I mentioned here in the description, we have essentially, I will provide some basic tools, okay, to really understand how to deal with superconducting circuits. Sometimes people ask me to develop a BCS theory for explaining superconductivity. And I will tell you now that this is not necessary tool for the things that we want to describe. I mean, of course, it is important to know that from the microscopic viewpoint, it is, of course, you need to know that when you cool down a sample and it behaves, becomes a superconductor, what really happens is that you form essentially a Cooper pairs in the ground state of the system. The Cooper pairs are bosons, so that you can they can condensate. And so in the ground state, we will have many trillions of or quintillions of Cooper pairs. Okay, so that essentially what emerge from that behavior. I mean, if you can try to study the BCS theory, try to understand how you form the Cooper pairs, but what matters for us will be the emergent behavior, and the emergent behavior will be something that we call a macroscopic quantum phenomena. Okay, and this is sometimes at least for me, when I was a young student of a bachelor or even a PhD student, for me was very I like it a lot to kind of build things from the very, very, very details from the microscopic behavior. But then you realize that sometimes there are emergent phenomena always in condensed matter physics. And for that, you don't need really to look at let's say the microscopic behavior of your system, but instead you may create effective theories. And this is the one that I will present in this lecture, because with this effective theory, that it is called macroscopic quantum phenomena, you will be able to really describe, for instance, the Meissner effect. You will be able to really understand why appears a supercurrent, superconducting currents in a superconductor, and that would be enough. Okay, so that would be my starting point. Okay, so essentially, I will talk about most of the time in terms of macroscopic quantum phenomena. Okay, as an emergent property of what really happens in the macroscopic at the macroscopic level in the superconductor. For sure, you'll see later. Well, this is something that I always mention in over the lectures, because sometimes it appears that most of the time the theory, the emergent theory that you will introduce in order to describe experiments has to be with bosons. Most of the time, we will talk about bosons, anharmonic bosons, oscillators essentially. And why it appears always oscillators is because at the macroscopic level you have Cooper pairs, and Cooper pairs are bosons. Okay, so for sure, the emergent physics that will appear at the global level has to be with bosons. It cannot be fermions, okay? Because in superconductivity you have at the ground state you have a lot of trillions of bosons that condense. And then, well, of course, I will provide those necessary tools for understanding the very basics things of superconductivity. As I mentioned, the Meissner effect, the explanation of why DC current flows around a loop, for instance, without any energy penalty, for instance. You can also explain this using the macroscopic quantum theory. And then this is what I will touch mostly in the first topic we have here. This is basics on superconductivity and Jesperson junctions. Okay, so here, as I mentioned, I will start my discussion using the macroscopic quantum theory. Indeed, you will see later that we will start from the Schrödinger equation, but we will introduce some new concepts and some ansatz for the wave function. You will see later. And this function is very successful indeed. Whenever you want to describe the emergent phenomena that happens. In a second topic, once we establish more or less the way to think the superconductivity for circuits, I will introduce the quantum fluctuations in electrical circuits. Okay, and specifically here in this topic, I will teach you how to build the Lagrangian and the Hamiltonian for an electrical circuit. So I expect that you are familiar with a Hamiltonian description of a system. Indeed, we will start with the classical description first, and then quantize, of course. And the quantization in this area has to be with, of course, almost always has to be with the temperature in the system. So we will see what will be the conditions for an electrical circuit to exhibit quantum behavior, essentially. And of course, it has to be with the temperature. I'm not sure whether you are aware of it, but essentially, you need to cool down your sample using those very nice refrigerators. Of course, you need to use cryogenic technology for that. And there is a very nice fridge where you cool down typically about 15, 20 millikelvin. Okay, this is the range. I mean, you have to keep in mind those numbers are very important. Okay, keep in mind those values for the temperature, millikelvin typically. Okay, for that we will see later the technical details, but at that temperatures and in comparison with the typical energy scales in the level structure of the circuits, you will see that we will reduce thermal noise, and then the circuit will behave in a quantum mechanical way. I mean, this is one of the probably, if you want to mention some complications in using quantum computers with superconductors, is that you need to cool down the sample, essentially. It's not that, well, at least at this very moment, you will not have a quantum computer in your or like a laptop, because otherwise, I mean, you need to cool down the chips in order for them to exhibit quantum behavior. Okay, we will enter into the details. Don't worry about that, and you will see why specifically when we put numbers, why we need those such very low temperature. Later in topic 3, we will cover essentially physical implementations of quantum bits. So nowadays there is a zoo of circuits, specific arrays of the capacitors, inductors, and just-as-one junctions that provide an energy structure, energy levels that are, of course, discrete energy levels. And we will study the different configurations, essentially, in the circuit, such that we create what sometimes people call artificial atoms, okay? Because we have a level structure which is discrete energy levels, and then because we have some unharmonicity in the system, it resembles the more or less the level structure in a real atom, okay? Here in particular, we will discuss one of the very first proposals for quantum bits, which is the famous Cooper pair box. Then there will be we will study the improvements of the Cooper pair box, which is the Transman, which is the right now is one of the I mean the most implemented qubit in the research labs, okay? Even of course in companies as well, like D-Wave. Although you see later that there are many proposals for quantum bits. We'll talk about the flux qubit, the fluxonium, etc. Okay. Then the topic 4, we will cover this coplanar waveguide resonators. So here we'll see how we will provide microwave photons in our system. And this is important because later on topic 5, we will put together quantum bits interacting with the coplanar waveguide resonators or LC resonators, so that we will start talking about this topic of circuit quantum electrodynamics, where essentially we have light matter interaction using superconducting systems, okay? And something which is nice here is that most of the models we use for describing light matter interaction in the optical regime will apply here for circuit quantum electrodynamics in the microwave domain. Although here is much more simpler because we will not have any for instance, what makes different from the real atoms with the superconducting circuits. In real atoms, you have polarization of the atom, huh? But in superconducting circuit, we don't have. We have coplanar waveguide resonators are essentially one-dimensional systems without any polarization, so that still the description will be very simple. Although it's simple, you will see that it is very good for describing real experiments. Okay, so then as soon as we finish this topic, circuit quantum electrodynamics, I will talk about a little bit on quantum simulators in superconducting circuits. It's a very hot topic these days. and you'll see later what people is doing right now, coupling many coplanar waveguide resonators to transmons and trying to implement paradigmatic models of the condensed matter physics, like the Bose-Hubbard model, for instance, okay, or the James-Cummings-Hubbard model. These kind of things we will touch a bit at the end of the course. I'm not sure whether you have some comments or questions until this point, Felipe.
No yet.
Okay. Well, I like a lot numerical simulations. I know already that you, Felipe, maybe Hamed as well, have a good background in doing numerics. Most of our lectures will be accompanied with numerical implementations. Say, for instance, we will diagonalize Hamiltonians. We will solve the Schrödinger equation to see some quantum dynamics, etc. Okay. For that, we'll use MATLAB, Mathematica, or Python, whatever you want. I have several codes, be in MATLAB or in Python, so that I will not teach you MATLAB, of course. Python, you know already, unless Hamed. I know you, Felipe. I know that you have expertise in those software, but if Hamed, but in any case, if we start again with the in-person lectures, whenever we have a lecture doing the coding, for me will be much more easier to have an online lecture, so that I will teach you the coding sharing my screen. Okay, that will be much more easier for you to see, and because I will have the code and I will record the lecture, so that you check again the lectures later at your pace, and then try to develop your own codes, etc. Okay, but most of the time, the way of I will evaluate this course, of course, is a PhD course, so that most of the work I'll try that is developed by the students. So I will provide essentially many handwritten homeworks, essentially. I will not, of course, as I mentioned, I will not ask for any PEP here, like that is called in such any examination. But for sure, we will work a lot doing homeworks, doing with both, combine both something with theoretical calculations, but also numerical implementations. Okay, that would, for me, will be very important, so that you really enter into the details of the circuit QED. And for instance, later you will know how when people try to speak about what a fluxonion is, you will know how to code the Hamiltonian for a fluxonion and diagonalize and see the spectrum of the fluxonion, for instance, or the transmon. Okay. And finally, typically I provide the students with a list of different topics, so that you choose one of them, and at the end of the course, you have to present a seminar reproducing everything that appears in the it maybe I can pass you an article, a paper, so that you reproduce the results and teach us how you did it, and showing plots and so on and so forth. Okay, so essentially that would be the dynamics in this course. So I will provide homeworks will be 80% of the course grade, and the seminar will be 20%. Okay. I'm not sure whether you have any comments here.
No, no.
Okay. Bibliography. Let me have a look. For the very beginning, say that the part that has to be with in superconductivity, I suggest the book number 6 here, Manjin and Kan. So superconductivity and introduction is very, very interesting, very intuitive and pedagogical way of introducing the superconductivity. It's very nice. With I mean, what I like of this book is it provides some history about the developments when it, for instance, they started speaking about the breakthrough that appeared in cryogenic physics with the experiments of Cameron Horns. Then start to appear describe, for instance, the London theory for explaining the Meissner effect. So there is a very nice. You can follow really the history how superconductivity was developed. And so I suggest this book number 6, to start. Of course, there is also this famous the Tingham, the Introduction to Superconductivity, which is a very nice book as well. This is very technical, I would say, but at least you have many references there therein. And I mean, you can also get some physical intuition reading the chapters. Okay. But for sure, I have my lecture notes that I will share with you, so that you don't have to write down everything. Well, of course, if you want to take notes, this is up to you, of course. But sometimes I mention some things during the lecture that are not written in my lectures, because I start thinking, and so that I mean you can complement my the course lecture notes with your own notes. Okay. So this is for the very beginning. So it's, I mean, for the topic 1, that has to be with the basics of superconductivity interception junctions, and then for the second topic, that has to be with the way of how to really treat with the circuit, meaning how to build the Hamiltonian of the circuit. This is the first reference we have here, which is Introduction to Quantum Electromagnetic Circuits. This is Uri Boole and Michel de Borret. This is you can really download it from the web. This is a full course on how to build the Hamiltonian of a circuit. Okay. Indeed, this is in the past, Michel de Borret had a course that he did in this famous Les lectures, where he introduces the famous spanning tree. There are some techniques, of course, to deal with the electrical circuits that well, we'll talk about in details, but it has to be with you start, for instance, one way to see how to produce or how to build the Hamiltonian is through the Kirchhoff laws, of course. I mean, in analog with a mechanical system, when you have, for instance, a particle, 1D particle, where you have the momentum, you have the position of the particle, And of course, you have the Hamiltonian fraction in terms of the momentum position. You know already from, I mean, in classical mechanics, you should know that there appear some generalized coordinates, generalized momenta, generalized coordinates in a system. So when you translate these ideas into the realm of superconducting circuits, I mean, whenever we have a circuit, we need to recognize what are the generalized coordinates. What would be the independent coordinates according to the, for instance, you know, imagine, or you remember your electromagnetic courses when you have a classical circuit and you apply the Kirchhoff laws. The first Kirchhoff law has to be with the conservation of the current, and the second Kirchhoff law that has to be with the sum of all the voltages around a closed loop has to be zero. And all this is condensed into you really, and later you will see that there is a technique. It's kind of I like to call like a Feynman diagram, because then later you will see the parts of your circuit, and then you will see I'll teach you to see I mean to really have a look to the circuit and then build the Hamiltonian, because it has to do with how you store energy in a capacitor, how you store energy in an inductor, or in a just-as-one junction. And there is a technique that appears in this reference that is a famous. It is called the spanning tree. Okay, I'll teach you later, because this will be, I mean, probably, I mean, all the parts in this course I would say I selected because are important, but this part is really, really important, because you, from here, if you want really later on, imagine that, I mean, you change the topic and you want to enter really into the details of superconducting circuits, will be very important to know how to build the Hamiltonian of a circuit. Okay. The second book is The Quantum Transport. It's Julie Nazarov and Jenny Blanter. Here as well, you'll see that I don't remember exactly the chapter, but there is a chapter that has to do with the implementation of superconducting quantum bits. I will not follow much this, but I mean, if you want to take a look, of course, similar to the Tingham book, you will be able to capture some ideas, some physical intuition, some concepts that would be important. Okay. The third book is Quantum Engineering, Zagoskin. It's also a very good book. I would say probably here you will have more. You probably, yeah, you will see not in very details the how to build the Hamiltonian, but they will provide a very wide view on all the types of superconducting circuits, superconducting quantum bits that we have right now. So it's very interesting as well, this book, Quantum Engineering. For this the fifth reference is Orlando Delane, Foundation of Applied Superconductivity. It's also very interesting for the first topic. That has to be with the basics of here you will find a lot of foundations of superconductivity, much more than I will teach you, because you will see if you go to this book, you will see that there is a full 2 or 3 chapters only discussing about the electromagnetic behavior of a superconductor, for instance, or you will see a chapter on the thermodynamics properties of a superconductor. Not that important, but not so important for our goal here, that will be try to really understand the emergent behavior, then how to apply this emergent behavior in order to build quantum bits for quantum simulator, for quantum computing. Okay. Okay. So with this, I mean, I finished here with the at least with the description of the course. Okay. I already passed you this information. So whenever you have any comments or questions, you just let me know. Okay. If you have any questions right now or comments, Felipe.
Not yet.
Okay. So let me, I mean, let me show you my lecture notes here, just to see. This is the type of things. These are my lecture notes, handwritten using the iPad. You see, I'll pass you all this information, okay? After I finish the first lecture, you'll see that it's full of many things are written here so that you can follow after my lectures, okay? See, this is the type of things that I'll share with you, okay? Here there are many calculations. For sure, I will perform some of the calculations which are more or less tricky, but then most of the details will be here, okay? So later I'll pass you this lecture. Let me start a bit now, entering more in details. Not only in details, but let me talk about a bit on the this is kind of an introduction, okay? And this presentation, of course, just to mention, this is the only lecture that I will present PPTs, okay? Later we will in the Blackboard, okay, and discussing things. So let me start discussing this introduction to superconductivity and just some injections. As I mentioned, of course, we know already that I mean the theory of superconductivity is very old indeed. The BCS theory, BCS because of the authors Bardeen, Cooper, and Schiffer. That theory for explaining the behavior of what we know as BCS superconductors was developed in the 1950 something. I don't remember exactly the exact year, but using that theory, people were able to explain most of the things that happen in the experiment. At the very beginning, indeed, there were only experimental results. In the book that I mentioned about the development of superconductivity, you will see that they start with discussing about this famous experiment by Cameron Holmes that I'll mention later. But then using the BCS theory, if you really develop the things in a macroscopic way of thinking. So in that case, what we know already is that when you cool down a sample, not any sample, it has to be very, very specific. There are many superconductors in nature. But what happens is that there is a kind of there is a critical temperature where the system exhibits some strange behaviors. And from the macroscopic point of view, we know that this has to be with the formation of Cooper pairs, where two electrons with opposite spin half, one half, of course, with opposite spin, they form a bound state. From the theory of quantum information, they form an entangled state, indeed, a maximal entangled state. With a total spin, for instance, it depends. There are different types of superconductors, but the very basics one is when we have two electrons with opposite spin forming a spin zero superconductor. Okay, and then you see that I mean, although you have electrons in your system, the emergent behavior is something that has to be with a spin zero. And then you realize that integer spins has to be with in nature. We know that we have bosons, and of course a Cooper pair is a boson. It behaves as a boson, and then if you have bosons, bosons can condense into the ground state, forming a very huge, say, macroscopic a macroscopic entity, very similar to the case of a Bose-Hubbard and Bose-Einstein condensation. Okay. So, but I mean, this is something that you know from the history of the development in physics. Sometimes people ask me to develop this theory, but as I mentioned, it's not necessary indeed for explaining the emerging behavior. I mean, you don't see when you talk with people doing quantum computing with fluxonium, you never ask about the Cooper pairs. You know that Cooper pairs are there, but what matters is the emergent behavior. Of course, because at the macroscopic level you have bosons. Of course, what has to emerge is something that has to do with bosons. Okay, and this is why we have a description in terms of harmonic oscillators or anharmonic oscillators always. Okay, this is for me this is very nice, because you have to describe really the macroscopic. You need only the emergent behavior. Indeed, in condensed matter physics, we have there are plenty of this type of things. There is a famous article by Philip Anderson, where the article, I'll share with you the article, because this is only an article that is without any technical things, just physics concepts, and where he talked about more is different. This is the title of the article. More is different. So meaning that at all levels you have fundamental things. So I mean, if you try to, I mean, you know quantum mechanics, you know how to solve for instance, the particle in an infinite potential, of course. But if you put together two of those particles and you try to imitate the behavior of how a table behaves, you cannot. I mean, or how the people think. I mean, the social behavior in terms of quantum mechanics, you cannot. I mean, you know the very basic things, but the emergence, because the systems are more complex, because of the interactions, because of the very nature of your system, you have an emergence of different behaviors. And for that behavior, you need theories, okay? So in that sense, it's also a fundamental theories that will explain the emergent behavior. This is the concept that I like to pass right now, okay? So sometimes some people feel that they don't understand superconductivity and they need a BCF theory, of course. Well, sometimes but it depends. I mean, it depends if you want to really approach different problems where you really need to know the macroscopic behavior. For sure, you will need to use BCS theory, of course. But if you are a more I mean, you are more biased for doing research in quantum computing and quantum simulators. It is enough to know the macroscopic quantum model. Okay. So at the very beginning, this is a historical plot here. We mentioned always mention here. We have this pen color. Oh, this is pen. Okay. So we have here this physicist here was owner of the Nobel laureate, of course. This professor is called Kamerlingh Holmes. He was a Dutch physicist. He developed many breakthrough experiments in cryogenics. And indeed, he discovered what is known as liquid helium. Okay. And at that time, people was trying to develop some, most of the time, studying the behavior of metals as a function of the temperature. Indeed, well, Kamerlingh Holmes discovered liquid helium in 1908, okay? And then in 1911, he was developing an experiment where it was submerged. I mean, he took a mercury and he submerged this mercury into this liquid helium, and then start to vary the temperature. So in this plot here on the y-axis, we have the resistivity of mercury and as a function of the temperature. And then something very weird happened here. And then what appears here that around a temperature of 4.2 Kelvin, okay, this is the temperature, 4.2 Kelvin, he observed that the resistivity suddenly dropped to 0. It's very small resistivity here. And at that time, this was a very strange experimental result. Okay, but this is a historical result because, of course, at the time, people didn't know that we have a superconductor here, but let's say this is the starting point of all the physics that has to be with the superconductors. And of course, well, later on was realized that there is a famous critical temperature that, well, of course, for mercury is exactly 4.2, where this metal above this temperature we have a normal metal, and below this temperature essentially we have a superconductor. The mercury becomes a superconductor substance, and then you see that the resistivity suddenly drops to 0. And well, this is not the only material that exhibits superconducting behavior, of course. And there are many other materials that where you will see this type of behavior. So indeed, for instance, here we have this is a table that I took of a book of Professor Juan José García Ripoll from CSIC Madrid. Indeed, he's writing a book that's not published yet. Okay, so I guess I hope This book appears soon so that I can share with you. But on that book, there appears this table where you see that there are many metals. For instance, aluminum you have here. Indeed, there is a full classification of the type of superconductors. I'll explain later what is the meaning of a type 1 or type 2 superconductor. But here we have, for instance, for aluminum, we have a critical temperature here, which is this Tc is the critical temperature. Below this temperature, aluminum behaves like a superconductor. It's 0.175 Kelvin. Later, I'll explain what is the meaning of this gap. But this gap is predicted by the BCS theory, for instance, in terms of energy. Well, this is the frequency scale where below this gap, the system behaves as a superconductor. Above this gap, the system starts again as a normal conductor with resistivity, of course. We have lead, type 1 superconductor, 7.2 Kelvin, 660 gigahertz for the superconducting gap. For mercury, of course, this is the famous, I mean, the exact number is 4.15 Kelvin, where this metal behaves as a superconductor, etc. There is also now niobium, which is a type 2 superconductor. 9.2 Kelvin is the critical temperature. You'll see later that for using superconducting circuits, typically what people use is aluminum and niobium. The reason for that is that those two materials are very amenable for drawing nice circuits. Okay. This is why the people, experimentalists, they choose aluminum and niobium, because you can really I mean, using lithographic techniques, you can really draw any circuit you want. I mean, you can really build an inductor, a capacitor, a junction using those materials. Okay. In the development of superconductivity, indeed, there also appear those famous cuprates that are sometimes probably you may hear about high temperature superconductors. One example is this one is yttrium barium copper oxide, where you see that the critical temperature is much higher than normal superconductors. By the way, let me mention that aluminum, lead, mercury, niobium, all those superconductors you can describe are BCS, are called BCS superconductors, because you can really explain the behavior of I mean, in terms of the microscopic behavior, in terms of the BCS theory, essentially. Until this very moment, there is no theory for explaining the microscopic behavior of high temperature superconductors. Okay, this is one example. Why people don't use those high temperature superconductor for building superconducting circuits, for building quantum bits, is because the difficulty of fabricating chips. Unfortunately, I mean, are not very you cannot really use those lithographic techniques for drawing nice circuits using those, because all those materials are ceramics, essentially. Okay, so this is why essentially people use, instead of choose aluminum and niobium. And indeed, for instance, most of the superconducting circuits that we will see, for instance, junctions are made of aluminum, oxide of aluminum and aluminum. There's a junction there. For instance, the coplanar waveguide resonators, people use in niobium, for instance. Okay. What are the most important things that you see, behaviors? These are the famous behavior in superconductors. We have two main effects when you cool down a sample. The very first thing that you can observe are the establishment of persistent currents in a superconductor. Indeed, this is for instance, if you have a ring here, and if you are able to induce some current, some magnetic flux around the loop, be with a magnet, be with an external inductor, for instance. Imagine that you induce a current there in a loop. If you induce DC current, so direct current, you will see that you can establish on the surface of the superconductor a persistent current, a superconducting current that flows without any energy penalty forever. If and only if you have DC current, okay? Indeed, of course, the superconductivity, whenever you have radio frequencies currents, oscillating currents, and you'll see that the superconductor behaves, there's some dissipation in the system, okay? But in any case, something which is really interesting here is that, I mean, whenever you establish a superconducting current in a loop, in a superconducting loop, the current cannot take any value indeed. And the values that we take in this superconducting current has to be consistent with this famous fluxoid quantization that we have in this equation here. So any flux that you will see later in details, that whenever we have a superconducting ring or superconducting loop, the flux associated with a circulating current is quantized. There is a fundamental quantity, C, which is the flux quantum, is phi naught we have here, which is the Planck constant over twice the electron charge. So this is a fundamental constant. It's made of fundamental quantities, like the Planck constant and the charge, the electron charge. And we'll see later that because of the establishment of superconducting currents, persistent currents, we'll see that there are quantum states that carry some quantized persistent currents indeed. And this is very interesting as well, because the establishment of those superconducting currents on the surface of the superconductor allow us to explain the Meissner-Ochsenfeld effect that probably you may have heard about it. So imagine you have a sphere here. The blue sphere is a normal, let's say it's a metal. So that, and then it is possible to observe, this is the observation is that if let's say the material, we are above a critical temperature, and we have an external magnetic flux, then you see that the magnetic flux goes through the material, essentially. But below the critical temperature, there is establishment of superconducting currents on the surface, and those superconducting currents create magnetic opposite magnetic flux, so that this is essentially when you study the electromagnetic behavior of a superconductor, this is essentially the behavior of a perfect diamagnet. There is a perfect diamagnet here, where and the reason for that is because you have persistent currents on the surface of your superconducting material, so that you observe this nice phenomena which is called Meissner-Oxenfeld effect. And we will see this in details. We will see starting from the macroscopic from the macroscopic quantum phenomena, starting from the Schrödinger equation, and with a specific ansatz for the wave function, you will see that we can predict this behavior. You will see that the magnetic flux decays as we enter the superconducting sample. You'll see in the equations, and we will establish the famous characteristic scale, which is the London penetration length for the system. Okay, I mean, this is everything. I'm just talking very roughly behaviors. Of course, all these behaviors have a support in a theory. Okay, that I explain probably tomorrow. I will start doing the macroscopic quantum phenomena. But everything here has a very good explanation in terms of physical intuition, and of course in terms of equations. Okay. So let me show you. Let me show you this first. I'll change the order. Wait. So in the table that I show you already, I mentioned that they are in terms of the BCS. There are two types of superconductors: type 1 and type 2 superconductors. And this is when you study the thermodynamic properties of a superconductor, you can draw this nice, those are phase diagrams. And here on the left panel, see we have a type 1 superconductor phase diagram. On the y-axis, you have the magnetic field. On the x-axis, we have the temperature. And you see that there is again, here you can describe there is a critical magnetic field and a critical temperature. Above those values, we have a normal state of a superconductor. So here, for a type 1 superconductor, whenever you cross those critical values, and if you apply a magnetic field, then the magnetic field will enter fully into the sample. Okay. But then if you are in this region where it is called Meissner phase, so we have here you have normal state and Meissner phase. So in this region, the superconductor expels everything, any super magnetic field. So here we have a perfect diamagnet in this case. Okay, so we have only two phases for type 1 superconductors. Okay, normal phase and Meissner phase. But also there are the type 2 superconductors. For instance, in niobium is a type 2 superconductor where we have 3 phases here. So indeed, there are 2 critical magnetic fields, H. So first of all, there is a normal state where if you apply magnetic field, the magnetic field enters the sample. That's it. So this is the normal state. But then there is a critical magnetic field where what we observe are, so we have a phase that is called flux lattice. So, and this is you can observe this flux lattice here on the right, here by side the panel B. We see regions with dark dots here. And this is very, very interesting because they are, when we have a type 2 of superconductor, what happens, for instance, below this, the first critical magnetic field is that sometimes some parts of the sample, the magnetic field can enter. And some part is spelled out, but some parts, the magnetic field can enter and create those vortices. Those are very famous, Abrikosov vortices are called, where you create indeed there are you penetrate some specific region of the superconductor and you create circulating currents around. But then if you change a bit again the magnetic field, you enter in a third phase, which is again the Meissner phase, where the magnetic field is spelled out. Okay, no magnetic field enters the sample. I mean, in this way, you can make the difference between type 1, type 2 superconductors. Okay, so this is why you can choose, for instance, the typical behavior is type 1 superconductor is aluminum. Type 2 superconductor could be niobium. Okay. Let me show you a bit on, yes.
About this slide, depending on the region, the resistivity of the sample will change also, right?
Of course, yes, of course. I don't have here a specific, probably there should be some specific phase diagram for resistivity, but yes, of course. There are regions where the magnetic field penetrates a bit, but typically what you create are vortices, and you see that on those vortices you have a quantization of the flux, for instance, the magnetic flux. This is the very typical phenomena that appears here. Those flux quantization vortices, and those are called Abrikosov vortices.
Okay.
I mean, this is interesting to know. I mean, because niobium, for instance, they use. But I'm really, experiment, for instance, this is a good question. I don't know the answer. I'm not sure whether when you have maybe we have to take a look at the temperature, but I'm not sure whether you are working probably you are working in the Meissner phase when you create the coplanar waveguide resonators, for instance. Maybe. I'm not sure about it. I'll check. But niobium, for sure, is a type 2 superconductor. So let me show you the last this last slide of this lecture today. This is the thing that we will try to at the end of the course. Right now you see this and probably you see nothing, but my hope is that at the end of the course, when you see this, I'll show you this slide once more, and then you will be able to recognize what is that. So here, for instance, on the left panel, you see this is the typical drawing using lithographic techniques for drawing a circuit. So not sure how probably.
You need to select pen because it is in automatic.
Place a pointer here. So have a look here, this on this panel we have this part which is gray here is typical is the insulator on top. This circuit is built. Usually, people use sapphire or silicon. Okay, and this part, for instance, this is this kind of you see this one in green line here. This is a huge capacitance. This is the way the people draw or build a capacitance. Okay, like this way. This is a capacitance, and you see here that there is in this part this is a squid. This is a loop. So this is a superconducting loop where we have just some junctions here. But this is this is a transmon qubit. We will study this in details. We will build the Hamiltonian for this system, and we'll see that there appear a level structure very similar, where we will have the two lowest energy levels. You can use those levels as quantum bits. But you see, then here you have this line. You see this line, and this is a microwave resonator, which is coupled to this device here. And because this is a metal, and between you have an insulator, essentially you have capacity coupling here. There is the electromagnetic field that makes the connection between this coplanar waveguide resonator. This is typically for doing some measurements that I explain later. There is also a microwave cavity here in green. You see this is a piece of metal which has some inductance and some capacitance, which is also coupled to this transmitter. You see, and then, so you see, we have a loop here. We have a superconducting loop, which is squid. This is essentially those letters are a superconducting quantum interference device. And then we have a closed loop, superconducting loop, and here we have just some junctions. This is the way the junctions they look like. See, and you have here is a very weak link where this is the pictorial representation of a junction. So we have a superconductor, insulator, superconductor. Typically, these junctions are made of the superconducting part is aluminum, and here in between we have aluminum oxide, okay, óxido de aluminio in Spanish. And the gap here is about 1 to 2 nanometers wide. This part is it's a very weak link that we have here. And this is very interesting because we will see later that we will study in details what are the features of the junction. You'll see that there appear some nonlinearities in my system, and because of this nonlinearity, we will see an anharmonic spectrum in the Hamiltonian for the circuit. So the junction will be one really important component for building superconducting quantum bits. Okay, I explain this in details later, but as I mentioned, my hope is that as we finish the course, you will be able to recognize all these parts in the circuit and to see really what is the qubit here, what is the transmission line, and so on and so forth. Okay, and we'll enter the details for this this type of circuits. Okay, so I'm not sure whether you have any comments or questions.
No, not really.
Okay, so with this I finished today. I'll share with you the lecture notes where you will find much more details. And tomorrow I will start discussing the microscopic quantum phenomena and more techniques, more technical parts. Okay, and to see how appears the Meissner effect, etc., etc. Okay.
Okay.
Okay, then. So see you tomorrow. Have a nice day.
See you.